Hello YouTube, this is Eli, the OBD Tech. I'm here working on a 1996 Buick Regal with a 3.8 liter engine. Customer complains that the vehicle has a check engine light. Alrighty, I already have my scan tool already hooked up to the vehicle. So let's take a look at the engine codes. Alright, so I'm gonna hit diagnostic trouble codes and see what we have. We have one code. It's P1441. Evap emission system flow during non-purge. This basically is telling me that the problem could be either the purge solenoid or maybe the evap vacuum switch for this vehicle. I already looked at the on the label, under the hood for the evap system, and this vehicle has a purge solenoid and an evap vacuum switch. So my focus will be on this on those two components. So now I'm gonna take it to the system's wire diagram and see how this system is controlling the solenoid and the evap switch. Alright guys, so we're here looking at the canister purge solenoid description and operation. On the description, it says that the evap purge solenoid valve allows manifold vacuum to purge the canister. The powertrain control module supplies the ground to energize the evap purge solenoid valve. Purge on. This means that when the computer supplies the ground, this means that this system is it's a ground side switch. The evap purge solenoid control is pulse width modulated or turn on and off several times a second. The PCM control pulse width modulation output is commanded when the appropriate conditions have been met. For example, the engine coolant temperature above 77 degrees Fahrenheit after the engine has been running about 2.5 minutes on a cold start or 30 seconds after a warm start. The vehicle is operating in closed loop fuel control. So those three operations have to be met for this system to be controlling the purge solenoid. And also on the operation, the canister purge pulse width modulation duty cycle varies according to the operation conditions determined by the mass airflow, fuel trim, intake air temperature, and the throttle position. Canister purge will be disabled if TP angle increases to above 70%. Canister purge will be enabled when TP angle decreases below 66 degree percent. So now I'm going to take it to the vacuum switch operation. Alright, so this is the evap vacuum switch. The evap vacuum switch is normally closed switch positioned in the purge line between the canister and the evap purge solenoid. The evap vacuum switch will open when the vacuum reaches to greater than 5 inches of water in the purge line. The evap vacuum switch is used by the PCM to monitor evap purge solenoid operation and purge system integrity. The evap vacuum switch should be close to ground with no vacuum present. 0% evap purge. With evap purge pulse width modulation at 25% or greater, the evap vacuum switch should open. So this vacuum switch is normally closed. It would open when the like I said, when it either reaches 5 inches of water in the purge line or the pulse width modulation of the purge cylinder is 25% or greater. Now let me show you, one more thing. Testing and inspection, which I think is very helpful for this diagnosis. Here in the bottom, it's saying that an incorrect evap purge system flow should set a DTC P1441, in which we don't have. A continuous purge condition with no purge commanded by the PCM should set a DTC P1441, in which we have. An electrical fault in the evap vacuum switch circuit should set a DTC 1442, in which we don't have either. Our main focus is at P1441. Alright, so I'm going to take you to the to the wiring diagram, just to confirm how this system is being controlled. The personal is being controlled ground switch, and the switch is is being the design of the switch is a pull-up design. Let me show you guys real quick, and then we'll do our diagnosis on these two components. All right, guys, so this is the wiring diagram for the evap switch and the purge solenoid. All right, on the purge solenoid, which is right here, like I said before, this is a ground side switch. The computer is, the computer is providing the ground to the solenoid, and then the feed voltage, which is a positive voltage, is coming from that 15 amp fuse. So always follow the wire that does not go to the computer, and that always determines if it's either a ground side switch or power side switch. In this case, it's a ground side switch. The computer is providing the ground for the solenoid. Now on the evap vacuum switch, just by looking at it, it's a pull-up design. The vacuum switch is normally closed, and the way to determine if this is a pull-up or pull-down switch design is the same thing. Always look at the wire that doesn't go to the computer. In this case, the wire that doesn't go to the computer is that pink wire. It goes straight to that 15 amp fuse, which is spliced with the evap purge, which is also pink wire. And the other wire is going to the computer. So this means that this, like I said, this is a pull-up design. Both wires, with the since this switch is normally closed, both wires should read 12 and 12. When you back probe both wires, so both should be approximately 12 volts. And on the solenoid, like I said, it's a ground side switch. Both wires should read also 12 and 12. And on a power side switch, both wires should read 0 and 0. On a pull down design, both wires should read 0 and 0. So in this case, we have a pull up design switch and a ground side switch solenoid. All right, guys. So let's go do our our test on these two components on our voltage checks to see if these both components are functioning properly. All right, guys. So I'm here at the engine compartment. I'm going to perform the voltage checks on the purge solenoid first. I already have my voltmeter back probing the pink wire, and that pink wire is our 12 volt voltage source, which is coming from that 15 amp fuse. And that pink wire should give us, with the key on, engine off, should give us approximately 12 volts. Here we go, guys. So currently it's showing 11.94, which is good. That means that our fuse is not blown. Now, I'm going to back probe the green wire with white. That's our ground wire. Like remember, like I said, this is a ground side switch. So I'm going to back probe it, and this should also read 12 volts. Alright, so it's back probed already. Voltmeter is showing 11.94, which is the same voltage as the pink wire. So this shows that the system integrity from the computer to the sensor is basically good. There's no opens or shorts. Now the next step is to back probe the vacuum switch and see those voltage on both wires. So I'm going to set up, and then I'm going to show you guys. All right, guys. So I'm here back probing the vacuum switch. Remember that since this vacuum switch is a pull-up design, both wires should read 12 and 12. On a pull-down design, both wires should read 0 and 0. But in this case, it's a pull-up. So the pink wire should read 12 volts, and the signal wire, which is I believe is a purple wire, should also read 12 volts. So I already have the pink wire back probe, which is coming from that 15 amp fuse, and it's showing approximately 12 volts, 11.92 volts, which is good. It means that that pink wire has no opens or shorts. Now the next step is to back probe that purple wire, which is our signal wire. Alright, so the purple wire is back probe already. So let's so the voltmeter is showing 0.03. So this right here shows that there's a problem. This wire should read approximately 12 volts, but it's reading approximately basically 0 volts, 0.03. So this means that this signal wire, it's either an open switch or there's a short to ground on the signal wire. So the next thing to do to actually perform is a bypass test by using a 12 volt test light. So by touching that signal wire and connecting your test light to to battery positive, this 0 voltage should jump to 12 volts. By doing this, this is going to confirm that the signal wire has no shorts to ground. And this, so if this 0 volt condition jumps to 12, our problem will be the vacuum switch as being the faulty component. So so I'm going to perform the like I say, the bypass test. But but in order to perform this test, this connector has to be actually disconnected. So I'm going to disconnect this connector, and then I'm going to perform the bypass test. All right, guys. So I'm ready to perform this bypass test. I already disconnected the connector to the vacuum switch. My voltmeters also connected to the to the signal wire. With the connector unplugged from the vacuum switch, the voltage is still basically the same voltage is still at 0.03, and that's normal. On a pull-up design with the connector unplugged, with the key on, engine off, the voltage should be 0, and that basically confirms that your circuit design is a pull-up design. For example, in other words, if this circuit was working properly, and if both wires were reading 12 and 12, by disconnecting this connector, that signal wire, which was reading 12 volts, should drop to 0 volts, and that basically confirms that your circuit design is a pull-up design. But in this case, like I said, we already backprobed that purple wire, our signal wire, and it's showing 0 volts with the connector plugged in and with the connector unplugged. So so I'm gonna do the the bypass test with the test light, which is already connected to my battery post, which is right here. So so it's on the positive feed of the battery. So if I touch ground, this test light should light up. So so I'm gonna perform that and just show you guys that my test light is hooked up properly. There you go, guys. This is with the test light touching ground. Touch it again. The light turned on again. So it means that my connector is properly connected to the positive post. So so here we go, guys. So by touching that signal wire with the test light, this 0 volt condition should jump. If it jumps to 12 volts, this basically means that our circuit integrity for the computer to the sensor, it's in good condition. There's no there's no opens or shorts. All right, so so here we go, guys. So so I'm gonna touch this the signal wire like this, on and off. As you can see, but just by touching it, our test light is not turning on. So it means that this signal wire has no shorts. It's not shorted to ground. But if this light did light, it means that the that the problem would be a short to ground on the signal wire. Right now what I'm doing, I'm touching the the signal wire on and off with the test light. So the next thing, I'm going to show you guys the voltmeter. While I touch the that purple wire. All right, guys. So here I go. As you can see, the voltage did jump to 11.97, approximately 12 volts. I'm gonna release it. I'm gonna touch it again. On, that's on, off, on, off. So this basically confirms and verifies that the integrity of this purple wire it's good. Like I said, no opens or shorts. So the main problem, it's a faulty evap vacuum switch. So the next now I'm going to show you guys another way with the with the scan tool. But to perform this test with the scan tool, your scan tool has to be like an enhanced scan tool, a scan tool that's able to do some bi-directional control. So I'm going to show you guys this other method to confirm that the signal wire is not shorted to ground, or probably has a open on that wire. So I'm going to set up and then show you guys this other method, with the scan tool. So I'm here with my scan tool already set up. I'm only showing the evap vacuum switch PID and the evap canister purge PID. It's currently on the evap purge on the evap vacuum switch. It's currently reading purge, and on the evap canister purge, it's reading 0%. On the vacuum switch, we're showing purge with the engine off. That should never read purge. It should be a non-purge at this moment with the engine off. That should be reading non-purge. But like I said, since our vacuum switch is faulty, the computer thinks that the switch is basically open right now, currently open. So it's basically thinking that the evap system is purging at this moment, and this is with the key on engine off. So like I said, I'm gonna do the bypass test with the test light connected to the positive battery post. Since our circuit is a pull-up design, if it was a pull-down design, our test light should have been connected to actually ground. But in this case, it's a pull-up design, so my test light is connected to a positive post. So I'm gonna touch the signal wire on and off with the test light, while we watch the scan tool on the purge value, and that value should change to non-purge. If it changes by doing this bypass, this basically is showing you that the signal and integrity of that purple wire from the computer to the sensor is basically good. There's no shorts or opens. So I'm going to perform the bypass, and let's see this PID on the vacuum switch. I touched it. It went from a purge to no purge. I released it again. I'm going to touch it again. No purge. Purge. And no purge. So this this method is another way to confirm your signal integrity by using an enhanced scan tool that's able which is basically able to do some bi-directional control, and also show you more PIDs, which is basically going deeper into the computer's parameters, which a generic scan tool cannot do. All right, so this, so I'm gonna replace the vacuum switch and then show you guys how a good system should work with the good switch installed. All right, guys. So after a trip to the junkyard, I was able to find a vehicle with the good vacuum switch. So this is the bad switch that was installed on this vehicle. It was basically open. The switch contacts were not doing its job anymore, which was open all the time. And I had the used a good working vacuum switch installed. It's not new, it's used, but it's doing its job. So currently I have the voltmeter already set up to the purple wire, which is our signal wire. With the key on engine off, it's showing 11.78, which is approximately 12 volts. And that's how a pull-up design should work. It should read 12 and 12 on both wires. So this basically confirms that our component, which is our vacuum switch, was faulty. With the known good one installed, that 0 volt condition that we had before on the signal wire is back to 11.78, which is approximately 12 volts. Now I'm gonna show you the scan tool with the key on engine off. The scan tool is currently reading on the sorry guys, it's too much glare right now. It's currently reading on the Evap vacuum switch. It's reading no purge. Like I said, that's how a good working system should work. With the engine off, that vacuum switch should be closed. This is a normally closed switch. So this pit should read no purge with the engine off, and our evap canister purge is at 0, which is also normal. Like I showed you guys earlier, on the repair manual, on the system's operation and description, this evap canister purge should start changing while it goes through some engine condition parameters, like temperature, closed loop operation, and some other key inputs. Alright guys, so this basically shows you two methods of going about this diagnosis, using either a scan tool or using a test light with the voltmeter. So so hopefully this video helps you guys do some diagnosis on a P1441 engine code on a GM vehicle. So stay tuned. Thanks for watching. Thanks.